Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. So I will start to deliver the lecture about determining evapotranspiration potential or reference evapotranspiration. As you can see, this is from the FAO handbook number 56. This is the procedure to calculate the reference evapotranspiration daily, okay, daily data. So please check page 72. You can see here that there is an example of how to determination of ETO with daily data. So this is the example of the given information. Please remember that when we determine the daily data, the daily reference evapotranspiration, there should be an information about the date, okay? What's the date? For example, here, July, and then the location, and also the geographical information, especially the latitude. As you can see here, this is the latitude is 50 degree, 48.9 northern hemisphere. Okay, north. And also there must be information about the elevation. For example, here the example is 100 meters above sea level. And then the weather information, temperature maximum, and then minimum temperature, and then relative humidity maximum, and then relative humidity minimum, and also the wind speed, and also actual hours of sunshine or the period of solar radiation or photoperiodicity. So these are the basic information required to determine the reference evapotranspiration of daily basis. As you can see, this is step by step of how to determine the reference evapotranspiration. First, you have to convert the wind speed, and then you should determine, okay, each step by step. Okay, so now I will present to you how to do this step by step with PowerPoint. Okay, so this is the step by step calculation of daily evapotranspiration with an example. Okay, so now, so I will not share screen because it's kind of complicated. So as you can see here, this is the given information. Okay, so the date is July 6, for example, and the location, the latitude is 7 degree 33 minutes south, southern hemisphere. And then the elevation, given information is 100 meters above sea level. And then the maximum temperature is 21.5 degree. Minimum temperature is 12.3 degree. Maximum relative humidity is 84%. Minimum humidity is 63%. And then there's a wind speed, which is 10 kilometers per hour. Okay. And then the sunshine radiation, 9.25 hours. So from the given information, the question is determine the reference evapotranspiration. So as we know that this is the equation given from the FAO handbook. Okay, so we will try to solve this problem step by step. Step 1, what we have to do is determine the T as T mean. The given information was T max and T minimum. So first we have to calculate the T mean. The T mean or T here, T is T max plus T minimum divided by 2. Okay, so we got T max plus T min divided by 2. So the result of the T is 16.9 degrees Celsius. So we get this T. Okay, the T is resolved. And then next step is determining the gamma. Okay, this is the formula to calculate the gamma. Okay, but however, we can use table 2.2 from the handbook. So you can search in the handbook. There is some annex about table. Okay, this is the meteorological tables given in the handbook. So from table 1 until table 9. From table 1, this is the P, but we will use table 2.2. So this is to determine the gamma. The information required to determine the gamma is the elevation. Okay, so from the given information we understand that the location is 100 meters above sea level. So we can find out from here z is 100 meters, so gamma, okay, so this is the table. Z is 100 meters above sea level, so gamma is 0.067. So it's resolved. Okay, gamma is resolved. T was resolved, gamma has been resolved. This next step, or the third step, is determining the delta. This is the formula to calculate the delta, or we can use table 2.4. The information required to calculate the delta is the T. Okay, this is the T. The T is 16.9. However, in the table 2.4, here, 2.4, there is no 16.9, but we have 16.5 and then 17. So, in the table 2.4, the number of the T was 16.9, is between 16.5 and 17, as you can see. So it's between here. So what we have to do, we have to interpolate. I give you the link here about how to interpolate. Okay, so sorry. I think I have to move this one. Okay, so this is how to interpolate. Okay, please check this link and please try to. So in this problem, for example, they are looking for what is the pressure for 37 degrees Celsius. So it should be between 3 and 5 because the given information is the pressure for 30 and 40 degrees Celsius respectively. So they do the interpolation to determine the pressure of 37 degrees Celsius. So please refer to this example about how to do this interpolation of temperature 16.9. So after we did some interpolation, we got the result that the delta is 0.122 kilopascal per degree Celsius. Okay, and we got this. So delta has been dissolved too. So we got the T, we got the gamma and the delta. And next is the next step, step 4, is determine the U2. U2 is the wind speed at 2 meters above ground surface. So this is the equation. Okay, so U2 is UZ. So this is the constant on elevation basis. We can use this equation or we can use table 2.9. Okay, if we go to the handbook, table 2.9 should be in page 222. So this is the conversion factor. The formula is still this one. So U2, this is the formula. U2 is UZ times conversion factor. This is conversion factor. So we have to check the conversion factor. Please remember that the given information is the elevation is 100 meters above sea level. Okay, so from table 2.9, we are looking for the, sorry, I made mistake. The wind speed was measured at 10 meter. 10 meter. Okay, 10 meter. The given information is 10 kilometer per hour. So it's equal to 2 because we will need information from the equation. U2 is wind speed at 2 meter height with the unit is meter per second. Okay, so we have to convert kilometer per hour to meter per second. How to calculate? You just go to Google. Example here. Convert kilometer per hour to meter per second. Okay, so here information is 10 kilometer per hour. How much meter per second? You put here 10 kilometer per hour will be 2.7778 meter per second. So we just change here. So many times you will not, the meter per second information is not given. So you have to calculate by yourself. Okay, so this is the wind speed, 2.78 meter per second at 10 meters. So from the handbook, we check the Z. The Z is the height of the wind speed measurement. Good. So this is at 10 meters, so the conversion factor is 0.748. Okay, so by using this formula, U2 wind speed at 2 meters is UZ, the wind speed at 10 meters times conversion factor. The conversion factor is 0.748. So the U2 is the wind speed measured times conversion factor. Okay, conversion factor is 0. This is the wind speed, 2.78. Okay, and this is the conversion factor. So we got this U2 2.078. So we got this U2. Okay, and the next is calculating the RES. ES is the saturation vapor pressure at the air temperature. Okay, so this is the formula to calculate the ES. Okay, so ES equal to EO saturation vapor at T maximum plus saturation vapor at T minimum divided by 2. where the saturation vapor pressure at the particular T is this formula. Or we can use table 2.3. Okay, table 2.3, minimum and maximum temperature. We understand that the minimum temperature was 12.3, where the maximum is 21.5. So we can, from the table, we can see, from the table, we can see that the ES of 12.3, we can do interpolation here. Okay, so after doing interpolation, we got that the ES of the 12.3 is 1.4 and the maximum is 21.5. So we got that the specific E vapor pressure for 21.5 is 2.564. So after adding the number divided by 2, so we got the ES is 1.7997. Table 2.3. Okay. Okay, so we got the number and then this is the table 2.3. And then next we got this ES. And then we calculate the EA. Okay, EA is by adding the humidity information from the saturation vapor pressure. Okay, so this was the calculation. Sorry, this was the ES. We use this calculation, the information given in the table 2.3. We use it here. We use here times humidity. Okay, and then after calculating, we got that the EA is 1.409. So EA is resolved. And next is calculating the G. Okay, G. G is the soil heat flux. Please note that the magnitude of the day or 10-day soil heat flux is very small. So we can ignore. Okay, we can ignore this. So the G of the daily soil heat flux is equal to 0. Okay, so we assume that G is 0. Next is calculating the net radiation or Rn. The Rn is calculated by this formula, which is the net radiation is short radiation minus long wave radiation. First, we should calculate the RNS, short wave radiation. Short wave radiation is calculating with this formula. 1 minus albedo times incoming solar radiation. First, we determine the incoming solar radiation. Incoming solar radiation can be calculated with this formula, okay, which is AS plus BS small n divided by capital N and times extraterrestrial radiation. It is recommended that we use A 0.25 and B 0.5. N is the actual duration of sunshine. It was given in the information. The sunshine is 9.25. Okay, so we got this 9.25, but how much is N? N is the maximum possible duration. Sorry, RA first maybe. RA is extraterrestrial radiation. RA is calculated with this equation, or we can use table 2.6. However, in this handbook, we miss table 2.6 and table 2.7. 2.6 to 5. 2.5. There is no 2.6. Okay. And also no 2.7. It goes to 2.8. So I searched for the table 2.6 and I found here. I will give file to you. Okay. I will send you the file of the table 2.6. So table 2.6 is the daily extraterrestrial radiation. You can see here in the table, the information given is northern hemisphere and southern hemisphere, and then the month, and then this is the latitude. So in the information given, we understand that the latitude is southern hemisphere, and then the date, the month is July. Okay, 7°33 of southern. 7, so 1 degree is 60 minutes. Okay, 1 degree is 60 minutes. So 33 minutes is nearly equal to 0.5 degree. Okay, I will send you how to calculate this degree. So 7 degree 33 minutes is nearly equal to 7.5 degree southern hemisphere. So we check here the southern, not northern, but southern hemisphere, and then check the July. The month is July, and the latitude is 7.5. So it's between here. July and 7.5. So we do some interpolation and we got that the LA is between 30.7 and 31.5. So after calculating the interpolation, we got that the LA is 30.9. Okay, 30.9. Next, so we got this RA 30.9. Next is N. Okay, N is determined with this formula, or we can use table 2.7. Table 2.7 is also missed. I will send you. But here we can see the table 2.7 is the mean daylight hours for different latitudes. Okay, so the information given is southern hemisphere and then the latitude, and this is the possible maximum solar radiation in one day. So we check the southern hemisphere for July, and the latitude is 7.5 between 8 and 6. So after do some interpolation, we got that this N is 11.63. So we got this N and we put them in this calculation. Okay, and the RA. So after calculating, we got that the RS is 20.01 megajoule per square meter per second. Sorry, this is per day. Sorry, per day. Next is calculating the RNS, or shortwave radiation, by this formula 1 minus albedo times RS. Okay, so first determine the RS. The RS is determined by this we already got this RS, right? The incoming radiation. RS is here. So we already got this RS. So we got this, we already calculated the RS, and then we can calculate the RNS. Okay. After get the RS here, 20.01, we can calculate this RNS. RNS is 15.41. And then next is calculating, because RN is short wave minus long wave. So next we calculate the long wave radiation. Okay, so the long wave radiation is calculated using this formula, or we can use table 2.8. Okay, by checking the T using the Tmax and Tmin and also the clear sky radiation. So we can use this table 2H, Stefan Boltzmann law. Okay, and we use the information of the 12.3 T minimum. We check the T here, 12.3, you can find out. And then T max, 21.5, here the information 36.96. 12.3, you can check the number and then calculate. So we got that this R and L, we get this conversion factor here is this one is 34.67. And then next we go to next step is calculating the Z. Z was given information, and then the RA. RA was also given. So we calculate this clear radiation, the clear sky radiation with the Z is 100 meters above sea level, and the RA has already given in the previous, this one, RA. Okay, so we got this RSO, and then after that, we calculate the long wave radiation. Okay, and then we got this, that the long wave is 4.91. And then after that, we back to the step, we got the Rn here. Okay, Rn is by subtracting RNS minus RNL. And then we got this Rn is 10.5, we put into this equation. And then after that, the final one, we calculate all. So we got that this reference evapotranspiration is 3.29 millimeter per day. Okay, so I will give you the assignment, and please use this step by step to calculate the reference evapotranspiration. Thank you.